microphone differently. This participant. Okay, good. Yes. So one more time, this work was done jointly with a number of people. I won't read them out again, but I think for completeness, I should. I think oh, it was the same than last. Yeah, but okay. So the second lecture on Eliashberg theory and its relation to holographic superconductivity will be concerned with, a little bit of a summary of what we did last time, because I know how my brain can only partially absorb all the important information. And when I give a lecture, I always repeat at the beginning, and that's why I get good lecture rating. Then you get in Karlsruhe a bottle of wine, a good wine. Well, that's what I'm trying to say, yes. So, and so then we will dwell into generalizations to finite dimensions and comment a little bit on, say, more incoherent system. But one more time, this was a slide in some version yesterday. Conventional theory, and this is done in order to frame what we are doing and what we are not doing here, maybe in clarity. There's a well-known microscopic theory. There was even before a well-established phenomenological theory. And what Gorkov in his 59 paper accomplished was to build a bridge between these two statements. And if you are a fan of Ginzburg-Landau theory, you can say, of course, trivial. Right, and you have all the rights to say so. There is a well-established approach to study quantum many-body systems and look whether they are superconducting. There was a much discussed description of holographic superconductivity and its description of superconductivity for critical system. And if you're a fan of this, you can say, why do I need a connection? Of course, this is trivial. And this trivial step is what we have been discussing. And the main purpose was, at least for me, as a motivation, this field lifted an extra dimension. And I simply wanted to know what on earth this extra dimension really is. And we have understood last lecture already that in addition to space and time variations of an order parameter field, the internal energy excitations of a Cooper pair can be probed at different energies. This is the frequency that belongs to the relative time of a two-time variable, not the absolute time, which is this one here. And if you just invert it, then you get this extra dimension. We looked at the specific model to come to those conclusions that goes under the name of the Yukawa SYK model. And this model is given here. It consists of non-dispersing fermions, here given characterized by a chemical potential, of identical Einstein phonons with some fixed frequency that's finite. So the bare problem of the bosonic theory is massive. And we have a coupling that is governed by a random interaction, and there are rules for the distribution functions that we had discussed. And in some cases you do, and in some cases you don't get superconductivity, depending whether the individual configurations do or do not break time reversal symmetry, as one might expect for a pairing problem. And then you get power law shaped correlation functions for propagators and of bosonic and fermionic system. And something I will have to comment on rather soon is that there's a so-called spectral asymmetry parameter, epsilon, that depends on the density that governs the spectrum. We have seen these branch cuts, and that was very nicely particle hole symmetrics, a picture I showed last time. And if you are changing the particle number from half filling, the branch cut peak is being pinned, continues to be pinned to the Fermi energy, but it looks a little bit asymmetric. And that is characterized when you analytically continuate this beast to the real axis by this parameter. We will see its implication in the holographic context in a sec. This system becomes superconducting. There's a parameter that is given by somehow the ratio of the mean square value of this interaction and made dimensionless by some phonon frequency. You can vary it. And superconductivity that starts off being quadratic in the coupling constant and then levels off at very high coupling constant and so forth. So that was the model we discussed. Yeah, there was, as we discussed last time, there was pair breaking parameter that induces some configuration that break time reversal symmetry. And if I make this a small correction, then not much is changed in this regime and significant changes occur in that regime. So this is the effect of pair breaking. One indication that different regimes, we'll get back to this later, of this phase diagram are very much differently sensitive to small perturbations. So this is a very fragile superconductor. We will also see it has a very small superfluid stiffness, and so that's the dashed line. Then what we also did is that we looked at the linearized gap equation of the problem that at low temperatures takes this very, very nice so-called gamma model form, something that was discussed in different contexts by wonderful colleagues of ours over the years. And this integral equation here for the gap, that where you see on the one hand the power law, the singular and scale invariant pairing interaction of a critical state, and its fermionic incoherence captured basically by these two factors, this integral equation with truly a few steps can be rewritten in the limit of this exponent not too far from zero in a second order differential equation. And it was, I keep bringing this up because we had no idea how this map could look like up until we thought, okay, now we have one differential equation. We know how the Klein-Gordon equation of a static problem in anti-de-Sitter space looks like. And then you just punch it in Mathematica and make a general relationship, and Mathematica tells you what the relationship is. And then we knew the answer, at least that there has to be, that the holographic variable is basically 1 over the energy that characterizes the relative time, number 1, and that the scalar field is related to basically an anomalous self-energy or an anomalous propagator. In the linearized theory, they are more or less the same, and some power law relation. And then there comes something pretty cute, namely that regardless of which universality class you have in the sense of which gamma value you have here, that's something that goes back to a question that Elia Koenig asked yesterday, you always get the same equation. And if you want, so the universality class is hidden in the value of the gap. If you are a holographer, that is utterly unsurprising to you, like everything that I'm doing is unsurprising to you, because they know if you solve this equation, it is an oscillator equation, logarithmic variables, hence it goes like power laws, and the power law is just given by the mass. So therefore your exponents are given by the mass. In our language, the mass is given by the exponents, right? Because we find those exponents to be something fundamental and worthwhile mentioning, while in the holographic description, I never had that feeling, because for them, the exponents is something that I can always tune by adjusting the mass of the problem accordingly. Right, so which critical problem you wish to study is just something, oh, you take this mass. Then after, in reality, indeed, something like 4 months after this first, or 5 months after we had this first idea, we then understood that the whole holographic map is a bit more complicated. So you have the anomalous Gorkov-Green's function, we're sitting in 0 dimension. It only depends on 2 time variables, no spatial variation. And we write it as function of the frequency that refers to center of gravity and relative frequency, omega and epsilon, Fourier transform with regard to one of these variables. And then we have this holographic map here where we also need to integrate over geodesics of the anti-de Sitter space in order to find the right mapping. And this is indeed the mapping between what we know from many-body theory and the scalar field that lives in a curved space and is governed by gravity theory. And a matrix that is behaving just as it should. Of course. You need to integrate over a curve, and this is the line element of the curve. Yeah. So this curve is parameterized. The red curve here is an example. is parameterized by the center point that lives on the boundary here and its radius. And then you integrate over entire zeta space along this geodesic, and the parameters of our field theory really determine only the integration contour along which you have to integrate. Yeah. So again, so from the perspective of a person who lives in entire zeta space, two neighboring, so for example, Sam and Pierce sitting very near each other, but this is only from the, say, poor perspective of our field, of our universe. In the actual and true entire zeta space, you guys are just nearby geodesics, right? We have also made this mapping in higher dimensional spaces where the analysis is a bit more complicated, but you can do this in just the same way. Yeah. Yes. Correct. No, I did not. Very good. So we are only looking at even frequency pairing here. So we have tailor-made the Hamiltonian that it doesn't have a solution that is odd frequency pairing. I chose a model that gives me only a solution that is even frequency pairing. You can, in the SYK literature, it's actually something that's been discussed quite widely, also create wonderful solutions that are odd in frequency. I don't know. We can talk about it if you have a good idea how to do this. I don't know how to do this, but I also haven't spent much time on it. It's an excellent question. These solutions are floating around there. They're interesting solutions, and it's perfectly worthwhile checking whether you can do something very similar. I'm pretty certain you can, but I just didn't spend much time on it because, well, I mean, it is yet another complication. There's so many things you only can do on a day, but it's a very good question. Yeah. Okay, so to summarize with this mapping that I've just mentioned, what we did was we started off from a normal state that's critical, governed by Green's function that are hidden in particle-particle bubbles and bosonic Green's function, did a Gaussian analysis of this problem, and then had a mapping, and this mapping then leads us to an action that in the variables that we've chosen here, so-called Poincare maps of entire zeta space, gives us the holographic superconductor as we wanted it. So therefore we have derived it in that sense, right? That was all something that we had discussed yesterday, but I felt it makes sense to go one more time over this. What we also discussed, and this is the last slide of what you had seen already yesterday, is that this very, very beautifully also generalizes to finite temperatures. And here we have not yet been able to generalize higher dimensional calculations that we will see soon to finite temperatures, because ADS2 is particularly kind to you if you want to look at it finite temperature. So what you can do is you use certain time reparameterization invariants to actually map the zero temperature solution on the finite temperature solution, and you use certain properties of entire zeta space transformations, and then you can find a rather lengthy but structurally very similar map between the anomalous propagator and the Green's function. I didn't even write it down because it's a bit too lengthy, and it found its way in the appendix of the paper. But in the end of the day, you find much the same holographic or map, where you now have, and that I find simply quite beautiful, where you know your scaling stops at temperature, and the way the theory tells the system to stop scaling at temperature is by putting a black hole there and giving us the metric that we know to be the finite temperature black hole solution of entire zeta space 2. And then the radius of the black hole is given by the Hawking temperature of the system. So you basically flow in temperature only up to hitting this black hole solution, and your superconductor is somehow sitting around this. And the student called it the order parameter atmosphere, which I find a cute word, right? Very good. So now you can also ask what actually happens to this covariant derivative here. So far, we've only taken it as a derivative, but it's a scalar field that is charged. And so you can ask whether there is some electromagnetic field, of course, that sits in 1+1 dimension that is hiding behind this derivative here. And indeed there is. You can show with rather straightforward mappings that there is a vector potential acting on our object. Now, this is a bit weird because we started out with something that I called a superconductor. But as we always do, we are cheaters. In most of our analysis, what we're doing is we're describing superfluids. The fact that these objects are charged objects will only rarely be taken into account. And that's, as we learned yesterday in Pascal's talk, we are so poorly educated on occasion with taking into account gauge invariance, right? So this is, we just treated the problem. The SYK model is super fluid in the strict sense because there was no need to have long-range Coulomb interaction, to have Higgs mode and so forth into account. So how come that all of a sudden now I get a scalar that lives really in a gauge field, and it is quite cute because I never understood the statement of the holographers. They say if you have a U1 gauge theory in the bulk, it corresponds to a global U1 on the boundary. And what we of course have is a global U1 on the boundary because we have charge conservation of our system, and it translates into a system that has a vector potential, and we can calculate this vector potential explicitly in a specific gauge. And what you find here is an electrical field. But the value of this electrical field is actually set by the charge density. So if you deviate from charge neutrality, from the perspective of this holographic superconductor that sits in bulk, it is a system that sits in bulk and feels an electrical field. So the finite charge density deviating from the particle-hole symmetric case is being communicated to this holographic theory by adding an electrical field. And the value of this electrical field you can actually find after a couple of manipulations to be expressed in terms of the particle density here. If you look at a wonderful appendix of an old paper from Antoine Georges, Olivier Pacolet, and Subir Sachdev. So because they solved a spin glove problem where the exact same analysis has to be done, that gives you the value of this field. Identification in this context here for holographic superconductor is what we accomplish. And the charge, of course, of this problem that enters here is again twice the charge of the fermion that you have for the that is govern basically the global U1. Yes. The black hole, I mean, the easiest way to understand it is when we do an RG calculation for quantum critical system, then the critical point is really being the flow only extends to infinity when we are right at the critical point at t=0, and we do know what to do when we are at an elevated temperature. We need to stop our flow when we are at the temperature. And in my naive picture, this black hole just does that. It stops the flow, right? And it stops the flow in an official manner. So there's a rather non-negotiable situation going on there, and then the flow stops. And there is, of course, an entropy associated with this. We had, I think maybe it was after the talk or during the discussion session, there's an extensive entropy related to the surface of the black hole, which is the entropy, the 0-point entropy of the SYK model, of course. Yeah. That's how I see it. There maybe. Right. Yeah. Very nice way. Yeah. Okay. So I mean, again, I did not understand a statement of the holographic community that they very well understood, that the that a local U1 in the bulk corresponds to a global global U1 on the boundary, our theory only has charge conservation, and that leads, however, in the holographic description completely naturally to the fact that the charge density is being encoded via an electrical field that acts in the bulk of the system. Okay, so be it. And then you can do something else. You can calculate observables. So what I can, for example, do, I take my superconductor and I'm coupling to the superconductor a source field that might depend on time. This source field, of course, corresponds to, say, coupling it to yet another superconductor via a Josephson junction, and J of t is somehow the time-dependent gap of that other superconductor, or whatever I can accomplish as a conjugate field to my order parameter. And now I have to follow my holographic map, and the rules are now well established. Start from it, do the mapping, interpret the data properly, and do a radon transformation and integrate over these geodesic. That's all not complicated, but you end up with an expression that's given here. So all of the mapping gives you a certain dependency on the radial coordinate. This is just the Fourier transform of what we feel to be the frequency dependent source field of our original bulk theory. And then there's some mixing of these that comes from the radon transformation and so forth. Important is this new field can of course be written in this wonderfully covariant manner again, and we can now utilize it to look at correlation functions. To some extent, that's a calculation that Piers wanted me to do for the fermions yesterday, but I only do this for the order parameter field. So you do an infalling solution into the black hole, you do all the analysis that the holographers told you to do. Now, to calculate the dynamical susceptibility of a superconducting order parameter of an Eliashberg theory is not something that I had seen done in great deal. Maybe there's one paper of Andrei Chubukov and myself from 2005, where in a specific case we looked into this, but this was not entirely trivial, and it's not something that's usually been done. Here, I can just do the following. I just go to the appropriate literature of the holography community, because they have done all of this. And it is even something that I could do again. It's doable. It's not very hard, because it's a Gaussian theory that just happens to sit in a funny space. And we can calculate the propagate of a Gaussian theory. And what you then get up is an expression for the pairing susceptibility that can be expressed in funny gamma functions and so forth and so on. So without really much work, just solving a simple boundary layer problem, you find, for example, here, this is from a paper from Iqbal, Liu, and Mezai from 2015. You know how the pairing susceptibility of such a system looks like. Something that you can, for example, use to reproduce or calculate a phase diagram. So there's lots of information here that I don't go into too much detail. So if you're right, this is our pair breaking parameter here. This is this BKT type vanishing of the superconducting transition temperature that we had seen already. If I go at finer temperatures through this transition here where we have an ordered ground state, you get from this funny expression good old-fashioned critical slowing down with a mean field divergence of the time scale with t minus tc, like you would expect for a classical transition. You can go here and be right at the quantum critical point. Now, this is a funny quantum critical point. It's very soft critical point. The susceptibility actually doesn't diverge, but the derivative of the susceptibility only diverges, because this is a very gentle critical point with this essential singularity here, and it diverges like 1 over logarithm. So this is the imaginary part as function of frequency of the dynamical susceptibility. Here's the central picture, 4 different points on the right-hand side here. And you see when you're away from the critical point, you have some linear behavior, and then it saturates. And here you have essentially constant response, and then it goes like 1 over logarithm. So this is a singular response at that critical point. Yes. Oh, well, just like the 1/x² one-dimensional Ising model has a BKT transition, right? No. It's just in the same. It just has the same flow equations. Yeah. Yeah. This is just so U and V is defined here. This is our boundary layer electrical field. This is temperature. This is charge. U and V. Gamma is our gamma. We know. Nu is essentially this is parameterizing the mass. I think it is square root of a quarter minus mass squared or something. So sorry about this. I should have done this more carefully. So this is designed so that the critical point is now sitting at 0. It's the pair breaking parameter in the microscopic derivation that we had, and the holographic literature just says, well, if you vary the mass, you get this or you get that, right? So so this is just a parameter that tells you what the difference is from this critical point, and it's chosen to be 0 at the critical point, but ultimately it's just our mass, which depends on say pair breaking parameters, for example. The orange region is the region, exactly. So this is the quantum critical regime where the susceptibility derivative diverges like 1/log. This is the ordered regime. This is the classical critical regime. And this is the regime where the susceptibility is particularly at low frequencies only linear and not 1/log. So what you would expect for an imaginary part of susceptibility. So this would be the crossover from the quantum disorder to quantum critical. Here you have a linear slope, and here you have this 1/log slope that is typical for this universality class to signal to you quantum criticality. No, I don't think it's a Fermi link. This is in the normal state is a quantum critical state under all circumstances. It's that the superconducting response of the system is not governed anymore by this critical point, but it's massive. So the superconductor is just massive, and you sense finite distance to the critical point. This is characterizing the superconducting pairing susceptibility. Yeah. It diverges it at the classical transition. It diverges not when you're coming from this side. What does diverge is only its derivative. It does not diverge when you're coming down from here, but again, its derivative only does. I was surprised by this too. When the student told me this for the first time, I said, go and check. It's nonsense. But of course, it was known to this community that this problem has this behavior. And this is this BKT type singularity here for this quantum critical point is a very soft one, if you want so. So there is clearly something singular, but it's not being reflected in a divergent order parameter susceptibility right at that point. At any finite temperature, it behaves just like at a classical transition, and it does diverge. The amplitude of this term just vanishes right at the critical point. You can also change the carrier density. And you look, for example, here at the real part of the susceptibility, and of course, it changes from being particle-hole symmetric to particle-hole asymmetric. When we see in the condensed matter context particle-hole asymmetric pairing responses, we typically think of preformed pairs or something. There's no necessary notion here of preformed pairs, but it's just telling us that the particle-hole symmetry of the underlying normal state is broken. That's been reflected by this electrical field, and that gives rise to this behavior. The main purpose of this slide is to show you results that you can obtain because you have made because you took advantage of the holographic literature and insights. So again, one could, in principle, of course, obtain all of these results just by solving the many-body problem. It's on the, say, SYK side of the problem. You don't need enter the Zitter language, but it's truly much, much faster to do it this way. Let's go to finite. Yes. Yes. Everything is a dot. Yes.
But at zero temperature, what is the dynamics of the basically fully damped wave?
At zero.
You can have
at zero temperature. I mean, this is a mean field theory. It's a fully connected dot, right? So you can't even properly define the stiffness. I mean, unless you need to maybe take one of your sides of your dot and ask how maybe the response, if you twist the phase there, how the feedback is on all the others on the average or something like this. This could maybe be done. So the question is whether it's algebraically ordered. This is just ordered. It has a finite expectation value that doesn't decay. Huh? At this point here, it is, I don't think it's algebraically ordered, but it probably, there is power laws, but there might be logs. I'm not sure about it at that point. In the ordered phase, it's just like any ordered phase. It's ordered. No. Well, I mean, zero dimensional in the sense of a mean field theory. If you take the Ising model and you have a fully connected Ising model, this is as much infinite dimensional as zero dimensional, right? And it's mean field theory that applies. Right. Yeah. So mean field theory is exact in this problem. At n equals infinity, yeah. So there's no, if you look at critical indices, for example, of this classical transition, it's all mean field. Yeah. So you can generalize the Yukawa SYK model to finite dimension. And this is, for example, a problem where we can do this, that goes, generalization that goes back to Kim, Altman, and Chow for Dirac systems. So what they say is, I have a Dirac theory that lives in 0, 1, or 2 dimensions. 0 dimensions, the theory would be identical to the one we've just discussed. But so non-trivial would be, say, 1 or 2 or 3. And on each, say, site, or for each space-time point of that theory, we have n degrees of freedom in addition to this, internal flavors. And these internal flavors, here with indices L and a little m, and the boson as well, which has a mass and maybe some dispersion, are coupling through a random coupling. But the random coupling is on every site, is translation invariant, but and the same for every site. So these models have the appeal that they are, or have the aspect that they appear to you somewhat artificial, and have the appeal that they give you controlled large n calculation of non-trivial problems. So this problem here has now not a critical phase in the conventional sense, but rather the coupling constant gives you a critical point from a system where you have an ordinary Dirac state to one where you get anomalous power laws characterized by new exponents. And then you have something that looks like almost ordered. And there's some, yeah, okay. So you can generate yourself a critical theory of critical fermions and bosons characterized by power laws that you can analytically determine as well. The logic is completely identical. And as long as you assume basically Lorentz invariant structure of the propagators, this problem can again be solved. And it gives you access to, say, if you now choose the interactions appropriately, and that what we've done now, you can solve this problem again against superconductivity. So what would this be? This would be some Dirac material that is exposed to bosons that through a strong electron phonon interaction, these bosons become optical phonons, become very, very soft. So maybe this is a Dirac system near a ferroelectric instability or something, because there are fans of this type of physics here in the room. And And now you're asking of whether this almost condensed ferroelectric boson can give us a superconducting instability. Now, a Dirac system, you can't do a controlled calculation in the coupling constant because you need the threshold interaction. But here we are having the large N as our control parameter. At least we can vary the coupling constant as we wish. And you find there's a critical coupling constant where you get superconductivity in that system. Yes. It would be, I mean, you can actually have both. Oh, yeah, you can. Unfortunately, I can't draw here because I didn't draw the phase diagram, which would be super helpful. So you have a coupling constant. You're going from 0. You initially have a state that is not governed by these exponents. They're all trivial. It's just a linear spectrum and maybe some small interaction correction. Your phonon stays massive. So initially, the phonon stays massive, and therefore, the Dirac spectrum just remains a Dirac spectrum with some short-range interaction correction. So then you have, and then you have a critical value of the coupling constant, and the system becomes superconducting. You have a Fermi liquid that becomes superconducting just because you've strongly coupled the system. You have zero density, right? It's just an interaction-induced effect where the strong interactions just mix particle whole, generate particle excitation. Then you tune the coupling constant a bit further, and then in the absence of superconductivity, you would actually hit a critical point where now the boson gets soft. At that point, TC actually goes up quite a bit. And then you get hit a critical point, and now you can ask at that point, what is the superconductivity of a critical Dirac system with, say, at the ferroelectric quantum critical point, right? If you go further in that theory, the ground state continues to be critical, which I think is an artifact of this model, because there's an ON symmetry of this problem that if it fakes you a Mermin-Wagner theorem. So, but the correlation length is exponentially large rather than power law large, and I think we know what this is the actual ordered state, right? The theory is just too stupid to know about it. Yeah. So. We can now look for superconductivity, and in this case, you find, and this is Veronica Stangier's work. We've done this together with Eliashberg. So the anomalous self-energy now depends on the in 2 dimensions, 2 space dimension, on this 3-dimensional space-time vector. And there is some angular momentum L equals 1 that dominates us, and it's longitudinal because this is a Dirac matrix structure, the self-energy, of course. It is longitudinal in this sense in the Dirac matrix space. So there is a well-defined superconducting solution that you can identify. And that's actually now the analogous calculation. We can go now from our space and time dependent problem. So we have space, we have time total, and center of gravity coordinates. And the center of gravity coordinates have a direction and have a magnitude, right? It's now a higher dimensional problem. The direction gets condensed into this L equals 1 longitudinal channel. So really the physics only depends on the magnitude of the relative distance between 2 space-time points now. And it is this variable that essentially plays the role of the holographic variable. So it is not necessarily the inverse energy, but it's the inverse space-time point if you have a Lorentz invariant system. The action with this map looks very similar. You have to integrate over geodesics. In the space, you have this additional dimension, and you have a certain coefficient up front. And then all of a sudden, say for a 2-dimensional problem, we end up in anti-de space ADS4. And the calculation is otherwise rather analogous. Yes. Mm-hmm. It does actually here. There's some angular momentum. There's an L equals 1 channel where this does. And this is, since it's an this is, if you want, so an orbital triplet. So yeah. So so coming from the gamma matrix structure of the problem. These are the internal orbital structure, because so our fermions having, so one can really think here rather of say graphene, where the Dirac structure is not a spin structure. Spin comes on top, right? So we have in the spin state a singlet, but we have an orbital triplet state. So so what I was confused about was the following. Initially we had only time-dependent objects. So we had two time variables in zero space dimension, and we could add them and take the difference. So we got the extra dimension. If I'm sitting in, say, d+1 space dimension, I have d+1 center of gravity and d+1 relative coordinates. So don't I get too many degrees of freedom, right? But it's really only that in these relative coordinates, you have a magnitude and a direction. And the direction you condense, because there are different masses or different attractive channels depending on these orbital degrees of freedom. And you condense in one of them, and only the magnitude matters, and that's your extra dimension. So it works all fine out. Correct. Yes. No, we haven't checked that. Yeah, we have only checked two space dimension.
Can you give us the reason why you have to average over the geodesic? You have to just take the blunt average, the DL, over the whole geodesic.
Yes.
Rather than where you transform, you take some object to get to the point. Just something free fall in the ADS2 averaging over time in free fall.
Yeah.
It just seems weird.
So again, the words I used yesterday were I think what motivated, I mean, first of all, the fact that you don't have a local one-to-one mapping from a field theoretical description to the anti-de Sitter space was suspected by Maldacena in some paper as one-liner. And you saw probably the radon transformation somewhere. I have no idea how this gentleman draws his conclusion, but that's what was said there. Oh yeah, 2017 or 18 or so, 19 or so, something like this. Yeah, it's very recent. And again, maybe to remind you, how did we stumble into this? We first didn't do the integration, and we thought already we had it, and we got signs wrong, one sign wrong in our metric, which I discussed yesterday, and it wasn't actually anti-de Sitter space; it was de Sitter space. And more importantly, and that's maybe the physics, if you express your source fields and boundary conditions in this de Sitter space, they are looking very singular. So anti-de Sitter space is much more pleasant to have your well-defined boundary conditions formed. And that's why you somehow physically are motivated by doing this. When your physical theory wants to live on some boundary of the system, and you want to glue your theory naturally to it, and that is more easier done in the anti-de Sitter description. They always start on the boundary and end at the boundary.
So in the infrared, it's a much longer.
Yes. Yeah. Well, I don't know. I didn't even remotely. To me, probably this aspect and the need for the radon transformation is the biggest mystery I still have. The words that one can use there is, oh yeah, it's all obvious because the entanglement entropy is also an extremal surface that sits on the boundary, and therefore it should be completely natural to have it. Those are the words that you find in these more recent papers that I just mentioned, right? But I haven't digested this. Yes, 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 yes. So, oh yeah, so therefore, the bottom line of the statement is these analogies carry over. And if for no other reason, I mean, I think this Dirac problem is already reasonably realistic. You describe an almost ferroelectric Dirac system near its critical point, and it's not an easy calculation to find a controlled description for this. Here is one, and it allows you in particular to address this problem as a system in anti-de-Sitter space 4 if you're right at the critical point of the quantum ferroelectric. I think this is very nice, and you get this whole anti-de-Sitter story. But there's another generalization to finite dimension that was also motivated by our, it's an optical phonon, and that optical phonon couples to the, once it condenses, gives our Dirac system a mass. So in the specific case of, for example, in the specific case of graphene, you want to ask which symmetry protects my me to be massive. Then you go to Bernovik's book, and there's actually a nice discussion of it. Now let me think. You have to break inversion symmetry, and so therefore the expectation value of this problem of this phonon will break inversion symmetry. That then it will induce you a mass. So that's. In the previous case, the holographic superconductor gave you a superconductor. No, this is a superconductor. What we're having is a superconductor that is caused by critical fluctuation of a phonon, but now we can give this phonon as it condenses a physical interpretation as giving being near a quantum ferroelectric transition. In the ADS. In the physical world that you and I and everybody else in the room lives in. The bulk is a holographic superconductor, the surface is a quantum ferroelectric. I have a model that I use to describe a quantum ferroelectric transition. At that quantum critical point, my phonon gets soft. I'm asking, what is the superconducting nature of the phonon-induced superconductivity of this weird state? And that superconductor is a holographic superconductor that sits in anti-de-Sitter space 4. The real world transition is a superconductor plus a ferroelectric. It's a quantum ferroelectric that has a critical point, and at that critical point, you're asking where it's not yet ordered, for example, right? Yeah, it's a okay. There's a quantum critical point that we can give some further physical interpretation, and that, as so often, is also causing superconductivity. That superconducting state is now an ADS4. When you solve this, you're going to have superconducting domes surrounding. Yeah, yeah. I'm upset that I didn't put the phase diagram. Everything would be so much clearer in our minds. I just didn't. Q equals 0. Yeah. So you can also go to finite dimensions, but look at compressible states. A Fermi surface, right? This Fermi surface, this was done here in this paper. Ilya still is a little bit covered and so forth. So these gentlemen looked at this model. It's a Fermi surface with a dispersion. There's a phonon again. It couples, and you can now solve the exact same problem. They did this on the this gets to momentum and frequency dependent Eliashberg equation at the saddle point with basically a compressible state that otherwise interacts through phonons. They looked at nematic instabilities. That's not important for our considerations. Yeah. Oh, wonderful question. Yes, you can in this new variable. So in this variable, without the minus sign, you can write down a gamma model again. No, it would not. It would not. Yes. Correct. You can. It would be different. It's actually between 1 and 2. It's above 1. But that's okay. The angular integration heal all the pain where there was the k minus k prime, there's the k plus k prime. As the response of the angular integration, no harm done. I was very scared that this goes wrong, but it's all fine. Yeah. Yeah, no, I did a mistake, and Veronica has often pointed out my mistake. And so if you write this in for this variable here, or actually for this variable, you can write down a gamma model type description, but the variable where you integrate is not frequency, but it's the Lorentz invariant magnitude of the space-time difference. And otherwise, everything looks the same. We used this trick to identify this exponent, of course. And what is the right map? Always, it's a one-trick pony, right? And the pairing is singlet and spin, but there's an orbital degree of freedom coming from the Dirac structure, and it is in this space. It's triplet. Yeah.
And the Bernoulli also it has psi has a spinor structure.
Yes.
A spinor structure. We like to follow the interaction.
So this is really gamma zero. So this psi bar psi phi, which means this is gamma zero. In other words, the boson doesn't have a spinor structure. It's a scalar object, but the electron phonon coupling in the Dirac language, going back to a good old-fashioned Hamiltonian, would be sigma z. So you have the kinetic energy with sigma x and sigma y in the kinetic energy, but the electron phonon coupling is that the phonon displacement couples to sigma z. Basically, if you displace your phonon, you displace the relative energies of the A and B sublattices, to think in graphene language. Is this answering your question? Well, he can yell, right? Yeah.
Yes.
So in this case, Ilya and company, they solved this problem numerically. They found that the self-energy is weakly momentum dependent and frequency dependent in the way you would expect for a certain one loop type of calculation. And the boson propagator behaves as you would expect as well. I now make an assumption. I'm taking the numerics and take the weak momentum dependence as momentum independence, and then do my machinery as well. And then I find, again, a holographic superconductor at the critical point of this phonon or nematic transition, if you want so. And this is, however, not in ADS4 if I lived in 2 dimensions. It sits in ADS2 cross R2, which is reflecting the fact that really only the self-energy only depends on time. So the anti-de-Sitter space appears to us as if it was a zero-dimensional problem with only time direction. And the spatial components of the problem remain flat. So this is quite important because it tells us in hindsight why we got always the same type of description than what was developed for compressible Fermi liquids, for spin density wave, charge density wave, and so forth type description, nematic transitions, ferromagnetic transitions. But it's also completely in line with what the holography people would tell us. What the holography people are telling us is, if you're starting at ADS2, but you enter the Sitter space has a finite charge density, at low energies near the black hole horizon, it looks like ADS2 cross SD. They knew all of this, of course, right? All what we are seeing here is when the holography people talk about so-called anti-de-Sitter fragmentation, which means at low energies, it looks like only the one direction is curved and not the others. In our language, it means the self-energy is momentum independent. It's a local theory, right? The Dirac system does not have a local theory. Space-time is clearly coupled by the underlying Lorentz invariance and so forth. So can you tell me when I should stop? Okay.
See if you can turn up your volume.
I don't know how to turn on any volume. I have a speaker here, my MacBook's. He can. Maybe you read it out.
Oh, sorry.
I see that Andre Bernwick is talking, but I just don't hear him talking.
Can you hear me? Can you hear me? We try later.
Yeah, I can hear.
Okay, you can hear. Okay, so yeah, so I'm wondering, with a lattice system that supports Dirac fermions, and that has to be not inversion, it's got to be C2 times T symmetry. Can you actually get that electron phonon coupling? So for example, in graphene, the electron phonon coupling couples to the Dirac spinner in sigma X and sigma Y, not sigma Z. So can you get a lattice model that actually has that electron phonon coupling, or is it, I mean, it's made up, it's fine. But from a model with C2T symmetry, which has to, in 2 dimensions, protect the Dirac cone, can you get from a lattice model of displacement a model that has sigma Z in the electron phonon coupling? Because the graphene one again has the intra-valley one, which is the one that you want, which is the Q equals to 0, and the one Dirac cone has sigma X and sigma Y, not sigma Z. If that was loud enough.
I understand the question. Oh,
Turn the score.
I understand the question. Sorry. Okay. Yes. Probably I don't know the answer off the top of my head. I thought, and Andre has thought about this more than I did, that all I need to do is move the on-site energies of, I mean, I can always, if I do this chiral symmetry breaking, I mean, quote unquote chiral symmetry breaking, that just treats the A and the B sublattice differently. There is an instability to the state driven by just
there's not a Dirac
Coulomb interaction.
There's not
so
a Dirac
I can
fermion.
mix this displacement that where the energy of the A and these two B sublattices are different. So there will have to be some mode that does this, but I honestly don't know the answer. Maybe that's the easiest way of dealing with this very, very good question. Because
it opens a gap if you break A and B sublattice symmetry, right? Inversion will open a gap.
I think
you have one Dirac, which is protected by C2T, not inversion, not time reversal. If your model is one Dirac, so it's got to be intra-valley electron phonon coupling, which is the Q equals to 0, 1, which you want for ferroelectricity, right? Yes. And then to start off with the Dirac, you need C2T, and then electron phonon coupling has to come out in a lattice model to be sigma X and sigma Y, I think. So anyways, but that's another story. But
excellent point. I owe you, if there exists one, a justification for this model. I don't have it right now. Yeah, very good point. There are 2 Diracs, and it would be, of course, the coupling constant would have to be opposite in sign or something for the 2. Yes, got it. Yeah, I was unmuted when I said that I owe Andre an answer to this question. I don't have it at the top of my head because he is absolutely right. The sign of the coupling constant would be opposite or something, right, for these 2 different. And I need to see whether I can realize this with 2 Dirac whether I can map the problem onto this one or not. It could actually work. Okay, but I don't know at the moment. So to summarize, what we have been doing here is we looked at a set of different models that had admitted an actual solution in some large n limit, and that allowed us, here's for example explicitly written again for the Dirac problem, and we had similar expressions for the say finite dimensional or 0-dimensional SYK versions with compressible states that flow to an effective description at low energies that are mathematically identical to holographic superconductivity. And by doing so, at least we have understood a little bit better what it means to talk about a holographic superconductor and what the involved variables are, and to some extent also put us into a position where we could use some of the knowledge of the holographic community to solve certain problems. So I will to spare you a few discussions here, and maybe want to show you one picture which is quite interesting. You can also ask yourself, how would the deep in the superconductor, how would the spectral function look like of the system? And this is here the superconductor itself. So far we have always stayed away from the ordered phase, but now let's just look how the superconductor looks like. And these are here now numerical solutions of the spectral function of such a superconductor, here at T equals 0 and here at some more intermediate temperatures. And what you find is, of course, the state is gapped. It's got a finite superconducting gap. 2 delta over Tc is somewhere 10 or something. It's a big number for this specific problem. But it's not just gapped. You also have the sequence of higher order bound states that forms in the system. And that, say, in a naive picture, you can somehow interpret that this superconducting state should not, like the BCS state, be considered an ideal gas of Cooper pairs, but there can be there are pairs, but you can also have higher order bound states of those pairs in some sense. And these are, in the specific case, you're not equidistant peaks. They give you bound states of pairs and higher order correlated structures and so forth. Now, early on, we thought about how one could measure this, because after all, there are lots of discussions of photoemission results and the cuprates, where you see this so-called peak, dip, hump behavior, and maybe this could be related to this in one way or another. But we will see this right away in the last topic that I want to briefly touch upon, namely how one can understand some of the superconducting states property in terms of this holographic language. And for this, I mostly want to discuss a slightly different perspective there where it's useful to use different coordinates. So whether there's a, say, gravity version of the superconducting state when we are actually ordered, even maybe with a small amplitude. And for this, I want to describe the anti-de-Sitter space with different coordinates, so-called global coordinates. They have the appeal that they explicitly show that the anti-de-Sitter space is actually bigger than what the Poincare coordinates manage to capture. Maybe in the most naive way, this is I started off as a hyperboloid, but I was always only on the upper half of the upper hyperboloid. It's actually more complicated structure. So you can find this is the region that we have so far been discussing in this set of coordinates, and but you basically can look at the problem as having basically 2 horizons in the problem. This was, of course, first pointed out as potentially relevant by Einstein and Rosen when they talked about their bridges and so forth. And in the natural coordinates for this problem are yet other coordinates, so-called Rindler coordinates. And this is the unreadable metric in the system, where you can somehow see that you have 2 horizons. That the manifold that the manifold of the solutions of the Einstein equations for this problem actually allow you to have 2 horizons, but they don't manage to communicate with one another. So one cannot send signals between them. There just happen to be different solutions to this problem. Fine, this is not something I'm even remotely an expert in, but I find it it is something that is well described and reproducible in the corresponding textbooks. But now it becomes interesting. There was a discussion here triggered initially by this paper from Gao, Jeffries, and Wall in 2017, how one can construct transversable wormholes in these systems. And what you really do is you take, say, an operator that lives on one side, and you take an operator that sits on the other side of some quantum theory that sits in this gravitational space. And if you have a coupling between these two objects, you get some energy gain that can basically give you the tension to open up a wormhole. So these solutions become more rich in the gravitational back reaction problem, and then you get basically wormholes that are traversable. Now, this general idea was then made very, very concrete by Maldacena and Chi in 2018 in the context of the SYK model. So they asked, what does it actually mean in the operator language that we are more familiar with to have a traversable wormhole? And in the language, they used Majorana fermions, but in the language of actual, say, charged fermions or complex fermions, this is nothing else. If I have two SYK models, they call it the left and the right one. I have two SYK models and I couple them with hybridization. If I actually do this, well, I give the system a scale. That's the coupling, and that scale gives you indeed in the gravitational language something very fancy, in our language something utterly trivial. Namely, there is you can couple these. The coupling between these two SYK models can be mapped onto the gravitation, a wormhole that communicates between these two gravitational theories. It describes the left and the right horizon in the problem. Now, what we can do is something very similar, and that is what we have been working on more recently. Let's look at our model one more time. Why did we introduce spin? We introduced spin so we can form singlets. So I don't need to call these objects left and right. Oh yeah, one thing is also important. These two SYK models had to sense the same disorder potential. Otherwise, this wouldn't work, which to some extent sounds very restrictive, right? But there is a realization of this in our model that is completely natural. Because, I mean, if you do believe in this disorder nonsense, at least it should be the same for spin up and spin down. So all one can say is, well, our left and our right holographic descriptions of the normal state are just the spin up and the spin down degrees of freedom that we use eventually only to form singlet Cooper pairs, because I didn't want to deal with odd frequency pairing. That's why we introduced spin in the problem. And then of course, if I have a pair, if I translate literally what Maldacena and Xi were doing, if I were to add a Hamiltonian between, say, C up dagger and C down dagger, modulus just a particle hole transformation in one of the SYK models, I actually am getting precisely this wormhole realized. But of course, we don't need to add such a term. We get it from spontaneous symmetry breaking. So we have that term produced. So in the superconducting state, at least as long as we are not too far away from the critical point, so this remains a small perturbation, so the order parameter, we actually generate spontaneously, if you want, so a wormhole. So our description of this holographic superconductor in its ordered state can be seen as a realization of a traversable wormhole of the holographic description of these two states. And then you can ask, so how do you measure this? This is something that was very nicely discussed in a paper here by Marcel Franz and collaborators for the Majorana SYK without superconductivity problem, where they calculated what the transition probabilities are. This would be the uncoupled system, everything relaxes quickly, and then you can oscillate information between these two states, which we wouldn't be surprised of. Well, you have a two-coupled system, right? It just hops back and forth. And So we can now translate directly how would we measure the transmission probability through the wormhole in the gravitational description in the experiment. And the statement is that you measure this through what in our case would be nothing else but the AC Josephson effect. So the AC Josephson effect will be measuring, and here we've actually calculated the AC Josephson effect as it belongs to this in our 2019 paper already. The AC Josephson effect gives you, from these peaks that we've just discussed, gives you a fine structure in the Josephson response of the problem, and it will be exactly the same oscillation between two superconducting, of the pairing state between basically these two coupled spin systems that are entangled that you can measure if you want so using this experiment. So if you want to find out whether there is an underlying gravitational description in your superconductor and you do not wish to trust the theorist, at least there may well be, through this approach, an experimental way to test of whether this is a natural description in the problem or not, because the AC Josephson effect of a BCS superconductor will be strongly damped. That we know because it's been calculated in the mid-60s and so forth. So maybe with this, I want to finish here and want to show you a few pictures that tell us that Anti-Deceptive space is everywhere. When I started first thinking about this problem, when I was actually at a conference in Shanghai, and I saw this wonderful building here next to the Museum of Art in Shanghai. And this is this morning, I had to go there and walk from there here, the identical picture of Anti-Deceptive space as you can see it at the King's Cross Station. So thank you so much for your attention.
Years ago, we were unable to deal with simple things like counting aromaticism on straight dimension curve sentences because there was a spin momentum blocking the line curve.
Yeah.
Does your left right trick work?
Yeah.
Overcome that?
Yes. Yeah. Very simple and trivial. You just shouldn't take too seriously what we call spin and what, I mean, it's just a different degree. You shouldn't take it as the actual spin of the underlying relativistic theory. Then you, of course, immediately lock spin.
Is that just a doubling can increase more on criticality? Spin theory. Could you, for example, imagine
Oh, yeah. So, I mean, so what you can take this Yukawa SYK problem. You call the boson a spin 1 boson that can couple to the added spin degrees of freedom in the usual scalar product way, Yukawa way, and then if you want to give the boson a finite momentum, you need to maybe introduce 2 different flavors of fermions that sit at different patches, if you want so, of your Fermi surface. And this way you could maybe endow this, and then you would have a quantum critical anti-ferromagnet.
just this is very, very much thing.
Yes.
ADS-TNT was there's not physics running backwards in time. So first, and the most mundane things haven't yet been done. So for us, the most mundane thing was the Pauli susceptibility of
Yeah. Yeah.
And that, how do you get that? How do you get a Fermi liquid with the Pauli susceptibilities in the strip?
Yeah, you can get a Fermi liquid in a very simple way by adding a random single particle hopping. I jumped over this right here. Well, in the ADS dual world, it would just be a much more complicated, it wouldn't be an ADS description, of course. The Fermi liquid, I don't know how to get this Fermi liquid out of anti-de Sitter space. The metric will be more complicated. Yeah, it would not be an anti-de Sitter metric that would reproduce, but you can construct a metric that is identical. That no, it's no. Elio? Yeah.
So you use somehow this analogy to this topic.
Yeah.
And
Yeah. Yeah, okay, the statement is only at particle hole symmetry. Yeah. I don't know what happens. These are really things that we did in the last 2-3 weeks. So, yeah. So, yes. Yeah. Any quantum number you wish to give. So if you have an additional quantum number in the system, you can call it left or right. You can call it, I had actually seen this Schmalian II paper a while ago, and had kind of felt, oh, it's not really right. Why do I have a left and a right system that feel the same disorder potential? So it didn't resonate naturally with me. But as soon as you think about the system as quantum numbers that you add on top of it, then it's very natural, and you could do whatever you want to do. Yeah. Mm-hmm. Again, what?
Oh, thank you. So, Joerg, I apologize if I missed this, but if we go back to your Yukawa SYK Hamiltonian, that's basically a trivial flat band, so non-topological, basically exponentially localized electrons in a flat band with some Yukawa SYK coupling, right, to the phonon. So, as far as I know, a trivial flat band in BDG, which obviously is you're far beyond that, has 0 superfluid weight. So, but you mentioned you get a small superfluid weight, right? Can I understand the process from which that happens? Because if I have an infinite mass, which your bare electron certainly has, then I should get a 0 superfluid weight. But somehow you're generating one, right?
Yes, of course. So in order to even talk about a superfluid regime, we need to add some actual kinetic energy. Otherwise, this whole thing makes no sense. I don't even know how to define a stiffness. Even in this case, it is a hairy thing. But the natural way we did it, you add a kinetic energy to the problem. Then you can define at least the current operator on this problem in just like everybody else who does these dirty mean field theories has maybe a sensible way to get a current operator or to have a stiffness. And what you then do is you say either re-gauge the hopping elements, or you introduce the current operator from one side to every other side and divide it by n, and that you call your current operator. So then you can define either optical conductivity or a stiffness, and only in this case can we even talk about the stiffness. There will then be a crossover scale. You see some phase diagrams here given by the value of this hopping element, where you then, of course, at lowest temperatures always get Fermi liquid, but you have still at least a window of opportunity for non-Fermi liquid regimes. And in this case, you see what the transition temperature is. You recover the BCS result, in fact, because the quantum numbers may not be momentum, but you still get BCS. And if you then look at stiffnesses, a natural way to define them would be, and I know I'm jumping ahead here, would then be to, for example, divide them by the kinetic energy. So because it is only, and then we see that the stiffness here in the right figure is basically tracking TC, like for any dirty S-wave superconductor. And as soon as you go into the non-Fermi liquid regime, the stiffness immediately drops, mostly because the optical the spectral weight, the conductivity of the system actually gets much reduced, and then there's not much optical weight to be transferred into a delta function. That's the physics underlying it. But in all these cases, we had to add some kinetic energy, otherwise the system doesn't even know what a stiffness is.
Thank you. Thank you.
Hopefully.
And we'll be back at 11:40. We did the full time just 20 minutes from now. Start on very, very
Ah.